Kinetics. Given the following mechanism, what is the overall reaction? So we discussed how most of the time what we've seen up to this point is you always have a reaction, or you're given the words and nomenclature to write your reaction. And we assume that it went from the reactants to the products and that's it. However, most of the time that's not really the true story. It doesn't happen in a single step. There's either 1, 2, or 3 steps that took to get to the end result. That's called a reaction mechanism, when you have these elementary steps, fast or slow, to get you to your overall reaction. So here we are given the 3 steps, what it took to get there, and we want to know the end result. So it just ends up becoming canceling out the things that are in there multiple times or adding up and the things on the similar side. So looking at this reaction right here. So we have 2 nitrogen monoxides in step 1 on my left side, and I have no more nitrogen monoxide anywhere else. So I have 2 NO gas, and I've used this up. Then I made dinitrogen dioxide in step 1, and then if you look, it got consumed in step 2, so this is gone. Then in step 2, I have hydrogen gas, not on the product side on step 2, but also on the reactant side of step 2. So this is going to add up to 2 H2 gas. Okay, and then I have water on my product side of step 2, and I have water on my reactant of my other product side on step 2. So I have 2 waters. So I used up my water, and I used up my H2. So then let's see what's next. Dinitrogen monoxide is made here, and it's consumed in step 3. So this is also gone. And then all I have left is my nitrogen gas, just the one on my product side. And that is my final reaction. What are the intermediates in the mechanism? What is the catalyst? So let's first define intermediate. Intermediate is produced, then consumed. So it's always going to show up as a product in a reaction, and then it's going to be consumed right away. It's something that helps the reaction move forward in a mechanism, but it doesn't end up showing up in the ending reaction. A catalyst is a reactant because it's something that is there to actually help speed up a reaction. So it always first shows up as a reactant and then a product. But it does not show up in the end reaction because a catalyst itself doesn't show up in your end result. It's there to help you. So it gives you a different route to go to get to your end result. So knowing that, let's look at what we got here. So let's just erase all of this stuff. And we see, alrighty. I already know in step 1 I made dinitrogen dioxide, and in step 2 I used it up. So that is an intermediate. And then I also made dinitrogen monoxide in step 2, and then I used it up. So that's another intermediate. When it's produced and consumed. Now, from my mechanism, I don't see a reactant that was first a reactant and then a product. I only see something produced and consumed and everything else maintained in my reaction. Therefore, I didn't actually have a catalyst in this mechanism. Now, next part says, what is the rate law? So, we've learned when given different rates and concentrations, we can determine the rate order of a reaction in the rate law by looking at the relationship between the concentrations of one reactant when the other is constant and solving for the exponent, the order. Now, that's when you only have one reaction because we don't know the steps that it took to get there. If we are given our steps, we can do it a little bit differently because the slow step here, also called rate limiting step, tells you what is limiting the rate the most. So it's telling you the most accurate data of how these molecules collided, how long it took. So for this reason, we can use that information to find the most accurate rate law possible for the overall reaction. So we always write the rate law based off our rate limiting or rate determining step, the slow step. So going off of that, we would write rate is equal to K, the rate constant, times concentration of H2 and concentration of dinitrogen dioxide. Perfect. Now, there's one little problem here. Dinitrogen dioxide is not in my end result. It is an intermediate. We cannot have intermediates in a rate law because that also doesn't give us the best representation of the rate because it's consumed and produced immediately. So we have to look back at our mechanism and solve for the rate of just this intermediate. Now, the only reaction that has that is step 1. Now, there's something unique about step 1. It's the only one that has a double arrow. It happens very fast. This double arrow means that the forward rate is equal to the reverse rate. They are happening at the same time. As dinitrogen dioxide is produced, it is decomposed back to 2 nitrogen monoxide molecules. So we can isolate and solve for dinitrogen dioxide. I can write, well, K1 times nitrogen monoxide squared is equal to K inverse 1 times dinitrogen dioxide. Since I want to solve for this, I'm going to isolate and move the inverse of K over. And I get K1 over K inverse 1 times nitrogen monoxide squared is equal to the concentration of dinitrogen dioxide. And now what I can do is use that here, plug it back into my equation. Then I'll get rate is equal to, I should have written K2 earlier. We always have to specify which K. K2, K1, K inverse 1 times H2 concentration and concentration of nitrogen monoxide squared. Now, this is perfect, but you can take it up one more step. Most of the time, we say, all right, well, I'm going to say my overall K, not 1, 2, 3, etc., just my rate constant is equal to my K2, K1 over K inverse 1, where then you can write your rate law like this. Rate is equal to K times the concentration of hydrogen gas times the concentration of nitrogen monoxide gas squared. So knowing when you want an overall reaction, you are trying to get rid of the things that show up on the reactant and the product side. Those can be subtracted. Anything on the same side is added together. An intermediate is a substance that is produced and then consumed in your steps. Those were just things that occurred. A catalyst is something that helps your reaction move forward faster. So it's a reactant because it's helping, and then it comes out as a product, so it goes away and doesn't show up in your end result. When looking for the rate law in terms of reaction mechanism, because you know the actual steps it takes to get to your end result, you always use your slow step, your rate limiting step, and write your rate law. You would be done. However, if you have an intermediate that shows up, you have to solve for the rate of the intermediate individually based off of your mechanism and then plug it in to get the overall rate law of the reaction. Now, looking a little bit more at kinetics, let's look at the Arrhythmias Equation. So we know that the Arrhythmias Equation takes into account the activation energy, concentration, and time. The original Arrhythmias Equation. We can plot data because we can find our rate constant and time and get data to help us find our actual activation energy. Now here in this experiment, there was a plot of the natural log of K, K being your rate constant, versus the inverse temperature, giving you a linear slope. This means that we have our natural log of K is equal to our activation energy over R times 1 over T plus the natural log of A. That is our Y is equal to mx plus b equation when it comes to plotting the natural log of the rate constant versus the inverse temperature. Now, you don't even really need to know all of that because you have your slope given. Your slope, which is m, is equal to the activation energy over R. We always know R, and we just are given the slope. So all you have to do here is cross multiply. You plug in your numbers, negative 7,445 K is equal to, Kelvin, negative of the activation energy over 8.314 joules per mole Kelvin. And your activation energy ends up being 61897.73 joules per mole. And most of the time that's in kilojoules, which comes out to be 61.9 kilojoules per mole. And that is your activation energy. Now you can use this data for other things. Since K, your rate constant and temperature, would be on your plot, you can solve for the slope. You can also get the intercept, so you can use these information to solve different things. The decomposition of SO2Cl2 in first order in SO2Cl2 has a rate constant of 1.42 times 10 to the negative fourth inverse second at a certain temperature. What is the half-life for this reaction? Okay, so you're told the term first order. So you base the half-life on the first order, which is T1 half is equal to 0.693 over K. Well, I'm given my K, so all we got to do here is plug it in. 0.693 divided by 1.42 times 10 to the negative fourth inverse second, and you get 4,880 seconds. Oops. Then it says, how long will it take for the concentration to decrease to 25% of its initial value? Well, if we're looking for the final, right, and we're saying how long will it take to get to its initial value, you use this and plug it in to get just the 25%. So this means that my initial, I should write it here, so SO2Cl2 is that. So I'm saying that this is actually equal to 0.25 of that. I know that first order looks like this. And plug it in. Okay, well, my ln of is 0.25 SO2Cl2 initial over SO2Cl2 initial, which cancels out, is equal to negative KT. Well, that would make this natural log of 0.25. Now again, the reason I did this is because it says how long will it take for the concentration of the compound to decrease to 25% of its initial value. So that means that my final here is equal to 25%, which is 0.25 of the initial. Since it's the final over the initial, both of them canceled, and you just get the natural log of the 25% is equal to negative KT. Now you know K, which is going to be negative 1.42 times 10 to the negative fourth inverse second times T, because you want to know how long. And when you do your math, your time comes out to be 9,762.6 seconds. If the initial concentration, so if I write it out, mine with a little naught sign is 1 molar, how long will it take the concentration to decrease to 0.78? So now I'm given my concentration at time t, 0.78, and I want to know time. So this comes out to be the exact same equation. I write ln SO2Cl2T over initial negative KT. And I plug in my numbers. Natural log of 0.78 over 1 is equal to negative 1.42 times 10 to the negative 4th times T. And T is equal to 1750 seconds. Last little bit. So now if the initial concentration is equal to 0.150 molar, what is the concentration? So you want the concentration at time t. You want this number at t is equal to 2.0 times 10 to the second squared. So now you want time. So up to you how you want to solve it. I like to separate back to my other equation. I know that the natural log, if I separate that equation, I get that the natural log of concentration A at time t is equal to negative KT plus the natural log of the initial concentration. So my natural log at time t is equal to negative 1.42 times 10 to the negative 4th times my time, 2.0 times 10 to the second, times, or plus, the natural log of my concentration, which was 0.150. And then I get that my natural log of the concentration at time t is equal to negative 1.9255. Then if you take the inverse, the concentration at time t is equal to 0.145 molar. So it's just using the overall concepts, knowing which equation. So since you were given that it's first order, it helps you solve. The most tricky one I would say would be determining this one. Since it tells you, okay, how long will it take for the concentration to decrease 25% of its initial value? Well, that means that your final is 0.25 less than the initial. And so if you write it like that, they end up canceling out and you already have enough information to solve the problem.